This is the fourth section of chapter 1, number theory, and this is about divisibility tests. Now, you'll see over here some rules that you may or may not know about how to test if certain numbers are divisible by a certain value. So for example here, if a number is even, we know it's divisible by 2. If it ends in 0 or 5, we know it's divisible by 5. If it ends in 0, it can be divisible by 10, and so on. So let's have a look at maybe some of the ones you may not have seen before. So how can we test if a number is divisible by 3? Well, if the sum, that's sigma, if the sum of all of its digits is divisible by 3, the number can be divided by 3. So you take the digits in a number, you add them up. If that number can be divided by 3, the number itself can be divided by 3. How can we test if a number can be divided by 4? Well, if the last two digits of the number can be divided by 4, the whole number can be divided by 4. I might do some examples of each one of these. So let's say we had the number 732, and we want to know if that can be divided by 3. Well, 7 plus 3 plus 2 is 12. 12 can be divided by 3, so that means that 732 is divisible exactly by 3. Let's go on to this one here. So the last two digits can be divided by 4. So if I just make any number up, 8, 7, 1, 2, 4, because these last two digits can be divided by 4, it means that the whole number can be divided by 4. To test if a number can be divided by 6, it needs to be a number which you can divide by 2 and by 3. So that means it needs to be an even number, but an even number which is divisible by 3. To test if a number is divisible by 9, then the sum of the digits need to be divisible by 9. So it's similar to this one here. So let's do an example. So let's say we had 7, 8, 3, 0. Okay, if I add those digits up, 7 plus 8 plus 3 plus 0, okay, that's 18. 18 can be divided by 9, which means that the original number is divisible by 9. Then the last one down here, to show that a number can be divided by 11, not 1, then the alternating sum of the digits can be divided by 11. Now what does that mean? So let's do an example. Right, so let's say we have this number 50,358. We want to test to see if it can be divided by 11. Well, we do the alternating sum of the digits. Now what does that mean? Alternating means plus, minus, like this. So we do 5 minus 0 plus 3 minus 5 plus 8. So we do plus, minus, and so on. So we see what that sum is. So that will give us 5 minus 5 is nothing, 0 adds nothing, that gives us 11. So the alternating sum is divisible by 11. That's just 11. So even if the alternating sum was 22 or 33 or any multiple 11, that proves that the original number is also divisible by 11. Now what's also useful in these divisibility tests is to be able to write decimal numbers. What I mean by decimal numbers, using the decimal system, decimal numbers as multiples or sum of multiples, multiple sum, let's call it multiple sum of 10, multiple sum of 10. Now what do I mean by that? So let's say I've got the number 17,384. Now I can write that number as 1 times 10,000 plus 2 times 7 times 1,000. So I'm writing it as a sum, as multiples of 10 plus 3 times 100 plus 8 times 10 plus 4. Okay, so we're multiplying by these powers of 10 here. And we can do that with any decimal number, and it's useful to write that in that form to help us solve problems. So let's call n our decimal number. And let's call the digits of this decimal number these an, an1, an2, and so on, up to we get to a0. Okay, so each one of these little things here represents the digits in a decimal number. So I'll just write that down. Okay, so digits in a decimal number. So that means we can split this number up. So this n here just stands for a number. So we can write the number as 10 to the power n times by the nth digit, n digit of the number, plus 10 to the power n minus 1, n minus 1. So you can see what's going on here. The power of 10 is equivalent to the position of that digit. So I go all the way to the end. We'll do 10 to the power 0 times by a0. So the position of each of these digits in this number is also the same as the power. So first digit, first position here, or 0 position, power 10 to the power 0. So we could think of this as a0. First position, or a1 position, a2 position, a3 position, a4 position. So the little sub number down here is the power of 10. So we can write a number in this form, and as I said, it's useful for when we're trying to solve problems to do with divisibility tests. Okay, so this question says prove that a positive integer n is divisible by 10 if and only if the last digit is 0. So there's a couple of things to point out here. If it says divisible by 10, then we know that we're dealing with mod 10. And this if and only if statement here, that's easy to miss. That means that we need to prove the statement both ways. Now, what statements have we got? Well, the statement we've got is that if integer n is divisible by 10, then the last digit is 0. So we need to do this. If an integer n is divisible by 10, then we need to prove that the last digit is 0. Yeah, a0 is the last digit. We also need to prove it the other way, that if the last digit is 0, that n can be divided by 10. Yeah, so we need to do both of these because of this if and only if. If you see that in a question, it means you need to prove it both ways. So the first thing we're going to do is say, right, let the digits of this integer be written like this, going up to a0. So that means that we can write n as powers of 10, so 10 to the power n, an, plus 10 to the power n minus 1, an1, plus dot dot dot. Let's just do the term just before the last one. So you've got 10 to the power 1, a1 plus 10 to the power 0, A0. Now we just need to remember that 10 to the power 0 is 1. So this last term is not a multiple of 10. Okay, so A0 is not, like all the other terms, a multiple of 10, and that's crucial to writing our proof for this. So n under mod 10 is going to be equal to A0, because under mod 10, sorry, this is going to be the only term that's not divisible by 10. All of these terms are divisible by 10 because they're all multiples of 10. And the sum of all of these multiples of 10 can all be divided by 10. So all of these terms here, the sum of those can be divided by 10. The last term can't. Right, so this positive integer written in mod 10 is just going to be the last digit, A0. So we'll now consider, what if A0 equals 0? Okay, so we're starting from this side of the proof to get to here. So if A0 equals 0, that's going to mean that n is congruent to 0, because we've just made A0 0 under mod 10. And we know that if something is 0 under a certain mod, that means it can be divided by that number, divided by the modulus. So this means that n is divisible by 10, and we'd write that as 10 divides n. Now, because of this if and only if, we've done this, we need to do the same the other way around. Okay, so start from here and work to here. We can sort of copy out our proof, but just the other way around really. So now we're starting with the assumption that 10 divides n. So if 10 divides n, that means that n is congruent to 0 under mod 10. There's going to be no remainder. If there's no remainder, that must mean that the last digit is 0. And that completes our proof, the if and only if proof. So we've proved that if the last digit is 0, the number is divisible by 10. And the other way around, if a number is divisible by 10, the last digit must be 0. Okay, so here n is a 3-digit number where n can be written in this form. So n is a decimal number because it's being written in powers of 10. And it says that a is not equal to 0. So basically this is a decimal number that's somewhere, or can be anywhere between 100 and 999. And what we need to show is that n, this 3-digit decimal number that can be any value here, is only divisible by 11 if a minus b plus c is also divisible by 11. Now whenever you see divisible by 11, something like that, we know we need to be working in mod 11. So let's start by writing down the information that we've been given, is that this 3-digit number can be written in this form. Okay, and this is actually in mod 10 at the moment. It's a decimal number. We need to change that to mod 11. Now the way we're going to do that is we need to work out what 100 and b are, and 10 are in mod 11. So let's take 100. We need to find out what they are congruent to. So 100 is 9 times 11 plus 1, so we have a remainder of 1. So 100 is congruent to 1 in mod 11. And how about 10? Well, 10 is 0 times 11 plus 10. So that doesn't really give us any extra information. We're basically going to end up if 10 is congruent to 10, because that's the remainder. But remember, we can find other congruent values by taking away the modulus, and in this case it's 11, by adding or subtracting the modulus. So I could add the modulus to this and get values congruent to 10, so 21, 32, 43 and so on. But it'd probably be more useful to take away 11 to find a congruent value to 10. So that will give me 10 is congruent to -1 in mod 11, which is more useful because if I look back at the question, there's like a negative there. So that's going to be more use than saying that 10 is congruent to 10. So now that we've changed n to a mod 11 number, n is actually congruent to, let's see, so a is 1, 100 is 1, so that's like 1a, I'll write that out like that. 10 is congruent to -1, so negative b plus c, so n is congruent to that in mod 11, so I probably want to just write n as congruent to a minus b plus c in mod 11. So I've changed the mod 10 number to a mod 11 number, or a number that it's congruent to in mod 11. Now for this number n to be divisible by 11, n needs to be congruent to 0 under mod 11. So I'll just write that down. So for n to be divisible by 11, in other words, this, n needs to be congruent to 0 in mod 11. Now we know that n is a minus b plus c, so that means that a minus b plus c needs to be congruent to 0 in mod 11. Now this last statement here means that a minus b plus c must be divisible by 11. Okay, so I'll just write down, so a minus b plus c must be divisible by 11, which we can write as 11 divides a minus b plus c. So we can complete our proof by saying that 11 divides n, which is the statement we've got here, if and only if, we'll just use the wording that's there, 11 divides a minus b plus c. Now remember, if we've got one of these if and only if statements, we need to show that it's true the other way. Now we've already proved it one way, so we don't need to prove it the other way. We can just say also, or you might use the word conversely, means the same sort of thing. Conversely, it doesn't mean the same thing, but conversely means basically going backwards. So also 11 divides a minus b plus c if and only if and only if 11 divides n. Okay, on this example, we go back to the rules that were basically right at the beginning that I gave you, these divisibility rules to determine whether each one of these numbers is divisible by the values given. So in A, if a number is going to be divisible by 9, then the sum of the digits also needs to be divisible by 9. So I'll write that down. So sum of digits needs to be divisible by 9. I suppose I could write it like this: 9 divides the sum of digits. Right, so let's do that then. We'll add the digits together. 7 plus 1 plus 4 plus 6 is 18. Now 9 divides 18, which means that 7146 is divisible by 9. So let's use the proper mathematical notation that 9 divides 7146. So have a look at B. So for B, a number is divisible by 6 if it's divisible by 2 and it's divisible by 3. So a number can be divided by 6, or 6 divides a number if it can do both of these things. It's divisible by 2, which basically means that it's even. That's the rule for testing whether it's divisible by 2. And it will be divisible by 3 if the sum of the digits is divisible by 3. Sum of digits is divisible by 3. So we're using basically the rules of divisibility for 2 and 3 to prove that it's divisible by 6. So first of all, 5838 is divisible by 2 because it's even. Or you could say because it's even, probably better the other way around, because it's even, it's divisible by 2. So since 5838 is even, 2 divides 5838. Right, to prove that it's divisible by 3, the sum of the digits needs to be divisible by 3. So we've got 5 plus 8 plus 3 plus 8. So it's going to be, that's 24. Okay, 24 is divisible by 3, or 3 divides 24. So that it means that the number 5838 is also divisible by 3. Okay, so now we can say since 5838, let's sort that 8 out, 5838 is divisible by 2 and 3. Therefore, we do the 3 dots for therefore, it is divisible by 6. So we can write 6 divides 5838. On C, we need to show that it's divisible by 4. Now the rules that something, or the rule that something is divisible by 4 is that the last 2 digits in that number should be divisible by 4. So 4 divides a number if the last 2 digits are divisible by 4, or a multiple of 4. Now if we look at the last 2 digits, which are 1 and 4 here, 14, 4 does not divide 14. Therefore, 4 does not divide 22619114. It's as simple as that. I only need to check those last 2 digits. Are they divisible by 4? And the last example, to find out if this number here is divisible by 11. Now the rule for divisibility by 11 is that we want the sum or the alternating sum of the digits. So alternating sum of digits is divisible by 11 if a number itself is going to be divisible by 11. So let's work that out. So the alternating sum is 8 minus 1 plus 3 minus 7 plus 4 minus 7. Now that sum of digits actually gives 0. Now 11 divides 0, doesn't it? Any number divides 0. Therefore, 11 divides that number. So 11 divides 813,747. And you could say actually that any number where the alternating sum is 0 will be divisible by 11. Okay, so on this question here, it says n is a 3-digit number, and here it's a decimal number. It's been spread out here, and the digits are going to be A, B, and C, and they're integers between 0 and 9, and A is not equal to 0. So we'll just underline that. So basically, this is going to be a 3-digit number, where it can be anywhere from 100. Because A can't be 0, all the way up to 999. So that's the first thing I'm going to write down. Now it says that n is divisible by 9. The sum of the digits of n is even, and n is congruent to 3 under mod 11. In other words, when this number is divided by 11, there's a remainder of 3. So let's go through each of these facts that's given, and we're going to write down an equation that we can use. So the first one, it says that n is divisible by 9. So 9 divides n, which basically means that the sum of the digits is also divisible by 9. Sum of the digits divisible by 9. Okay, so what would the sum of the digits be? Would that just be A plus B plus C? A plus B plus C. Now we could just write down, is equal to 9 times something. But there's actually only a finite number of values it could be. So we're going to use like exhaustion to list them. So if it's divisible by 9, the sum of the digits is going to be a multiple of 9. So like 0, 9, 18, 27, 36, and so on. Now, if we think about it, the sum of the digits can't be 0. That would mean A, B, and C are all 0. And we're told that A is not equal to 0. So we can cross that off our list. Could the sum of the digits be 9? That's possible. So the sum of the digits could be 9. Could the sum of the digits be 18? Yes, they could be. Could the sum of the digits be 27? Yes, they could be if they were all 9s. But they can't be any more than 27 because the highest they can be is all 9s. So actually there's only a finite number of equations that we can write down, and we'll write these down as A plus B plus C equals 9. Let's write this correctly. A plus B plus C is 18. A plus B plus C is 27. So there's only 3 possible choices for the sums of those 3 digits to make it divisible by 9. So in these 3 cases here, the sum of the digits is divisible by 9. So that means n is divisible by 9. Okay, let's go to the second piece of information here that says the sum of the digits is even. Now, if the sum of the digits is even, that means that n can be divided by 2. And also, if we look back at the 3 equations that we've written down, in only one of them is the sum of the digits even, and that's this one here. So now with this extra bit of information, we can cross out these 2 equations here. So we can cross out this equation because the sum of the digits there aren't even. the sum of the digits here aren't even. So this now just leaves one equation, which is a plus b plus c is equal to 18. So we can tick these off because we've used those. And we'll highlight this equation here. Right, if we go on to the third piece of information, n is congruent to 3 under mod 11. Now what does that mean? That means that when this number n is divided by 11, there's a remainder of 3. Okay, so we'll write that down. When n is divided by 11, or a multiple of 11, that could be negative 11, negative 22, there is a remainder of 3. So let's write down what those numbers could be. Now for things that can be divided by 11, we've already shown that the alternating sum of numbers that can be divided by 11 is 0. If there's going to be a remainder of 3 when a number is being divided by 11, it means that the alternating sum of the digits, is equal to, or is congruent to 3 under mod 11. That basically means when you divide by 11, there's a remainder of 3. So the alternating sum of the digits will be a minus b plus c is congruent to 3 under mod 11. Now, if we go back to this as if it were a decimal number, what it means is the alternating sum of those digits, a minus b plus c, has got to be a sum. Now we're talking about decimal, mod 10. It's got to be a sum such that the remainder when divided by 11 is going to be 3. So for example, if the sum of these digits was, let's say 14, yeah, that would give you a remainder of 3 when this number is divided by 11, because it's 3 more than 11. It could be that the numbers are 20, some could be 25, because again, the sum of these digits would be 3 more than a multiple of 11. Now we don't need to keep on adding 11, we could subtract 11. So it could be that the sum is 3 if we subtract 11 from 14, and if we subtract 11 from 3, that will give us negative 8. Now like before, when we did up here and we listed some numbers, are there any values here that are not possible? Well, what's the largest value we can get? We're adding a and c, and we're subtracting a number. So even if b is 0, the largest value we're going to get is going to be 18. Yeah, we can't get a number bigger than 18. So we're going to cross this out, the 25. And we're not going to get a value less than negative 9. Even if a was allowed to be 0 and c was 0, the most you can take away is going to be 9. So there's no point going, for example, to negative 19, because you're never going to get that value if a, b and c can only be from 0 to 9 and a is not equal to 0. So that just leaves these two options, that the alternating sum is either 3, 14 or negative 8. So I've written here those 3 equations. So now we've got 2 sets of equations, this one and these 3. And what we're going to do is we now can solve them simultaneously. And because the b has an opposite sign, we can just subtract one from the other, and get values for 2b. So I'm going to write the equations like this. We've got a plus b plus c equals 18, and we're going to subtract a minus b plus c equals, now I want to write down the different values, -8, 3, 14. Saves me writing out 3 sets of equations. Right, so if I solve those, if I subtract one from the other, I'll get 2b equal to, so -8 minus, 18 minus -8 is going to give me 26. So 2b could be 26, or it could be 15, or it could be 4. So they're the possible values for 2b. Now, since 2b isn't, or b is an integer, it can't be 15, because you can't do 2 times a whole number to get 15. And since b is between 0 and 9, yeah, this is one of the digits of this 3-digit number, we're not going to get 26 because b would have to be 13. So we'll cross that one out as well. So the only possible value is that 2b equals 4, which means b equals 2. And that came from when we had a minus b plus c equal to 14. So now we can cross out the equations where we don't get solutions that work. So we'll cross that one out there, and we'll cross this one out here. So now we know that the middle digit of our 3-digit number is a 2. So we know that b is a 2, like this. Okay, so from that we will have a plus c equals 16. So now, by exhaustion, so we can go through the digits that a and c could be, and we're going to pick the digits that add up to 16. So down here is a list of the digits we've got to choose from. Now, since the sum of the digits is 16, there's no point looking at any of these digits down here, because you would need to add at least 10 to one of the digits to get a total of 16. So none of these are going to work. Yeah, so we'll cross all of those out. So that just leaves 7, 8, and 9. Now the pairs that are going to add up to 16 is if A and C are both 8, or when A is 7, C is 9, or the other way around, or when A is 9 and C is 7. So now we have the possible values for n, and what we'll do is we'll write those possible values of n up here. Possible values of n. So we know the middle digit is a 2, so we'll start with this. So the first and the last digit could be 8, so 8, 2, 8. Then the first digit could be a 7, then a 2, and then a 9. So it could be 7, 2, 9, 7, 2, 9. Or it could be 9, 2, 7. So there's only 3 possible options for this number. And if you were doing an assessment, what you might do is actually just spend a bit of time just checking that these numbers here are actually divisible by 9. The sum of the digits is even, and if you divide them by 11, you get a remainder of 3. Right, so you should now be able to do exercise 1D on pages 18 to 20. We'll just do a quick recap here. So first part of the recap is the rules for divisibility, which you need to know about. You also need to be aware that if you have a decimal number, it can be written in this format. Let's say it was a 4-digit decimal number, so it'd be 1000A plus 100B plus 10C plus D. You also need to be able to interpret things like this. So let's say, for example, this 4-digit number that we're talking about had this statement. So you need to know how to interpret that. So for example, basically what it means is that the sum of the digits here, when this number is divided by 9, there's a remainder of 2. Now we know that when a number can be divided by 9, the sum of the digits can be divided by 9. So if I was going to interpret this, it means that A plus B plus C plus D, I could write down is congruent to 2 under mod 9. So I think if I think about that in terms of a decimal number, it means that the sum of the digits needs to give me a remainder of 9 once it's divided by 2. So some examples of what the sums of the digits could be. So it could be 2, because that gives you a remainder of 2 once it's divided by 9, or 11, or 20. So I could keep on adding 9s, or I could keep on taking away 9s. So some other possible values are -7, -16, -25, and so on. But there's probably going to be something in the question which is going to allow us to cancel out some of these values because they're not going to be valid.